So I just want to go back to here, maybe something that I didn't have made clear. So the final, okay. I just want to go back to here and about circular motion. I want you to understand that this is here, the velocity is always tangent to the trajectory. So let's say you have a circular motion like you can have in, like this is a vinyl here. So it's going to spin at a rate of 33 revolutions per minute, for example. So if you have like a dot here relative, and then you have another dot here, you have to understand that this velocity here is called the linear velocity. That velocity is going to be tangent to the trajectory, okay? And it's going to be larger, the largest one relative to this one. So even though all those points here, including the one at the center, they all spin at a rate of 33 revolutions per minute. Okay, so they all rotate with the same rotational speed. Okay, so rotational speed, you can have that in radians per second or revolution per minute, for example, or degrees per second. Okay, so they all have the same spin, okay, rotational speed, but the velocity is not the same. So this is called the linear velocity. And you have a relationship between them. The linear velocity equals the radius times omega. So in that case, omega is 33 revolutions per minute. So it means that if you are at the center, what's going to be the velocity at the center? 0, right? Omega is not 0, but the velocity is 0. So that means that something is standing here at the center. It's just going to rotate here, but it will not cover any distance. Okay, so I wanted to make that clear. Okay, so let's go back to Newton's second law. Okay, so Newton's second law says that for the same, so F equals ma, okay, so that means that for the same force, the acceleration is inversely proportional to the mass. So you multiply the mass by 2. For the same force, the acceleration will be divided by 2. So the mass is inertia. Okay, it's the laziness, resistance in changing the velocity, the changing the state of motion. Likewise, here for the same mass, the acceleration is proportional to the force for the same mass. So if you multiply the force by 3, the acceleration is multiplied by 3. Okay? And also for the same acceleration, so for example, here you have people in an airplane, they're going to take off, right? So acceleration will be about 30% of g, like gravity, okay? So about 30% of g, the acceleration to take off for a commercial airplane. So for the same acceleration that the three of them will experience, if the mass is larger, then you need a larger force, right? So for the same acceleration, if you increase the mass, you have to increase the force, which means that those three people will not experience the same force pushing on them. Okay, so the chair here is going to push on them so they can reach the right speed. The force experienced by the lady here will be larger, obviously, than the kids. That's why sometimes you see the kids in the airplane, they don't seem to be annoyed by that force. Yeah, they just stand there. Okay? So what does it mean? If the acceleration is 30% g, you will experience 30% of your own weight. So if your weight is 100 pounds, you will experience 30 pounds pushing you, okay, when it's gonna accelerate until the speed is reached. Okay, so that's why if you have a heavy person, for example, the force experience will be very large. So it won't be that comfortable. So I wanted to make that clear. And then here I told you that F equals ma, that's the Newton's second law. But the way it was written in Principia, which is a very famous book, the most famous book in science, Principia by Newton, he wrote it this way: apply a force, okay, during a time t, then you're gonna get a change in velocity, okay? The change in velocity could be faster, slower, or turning, okay? It doesn't have to go slower or faster, you can just turn. But how much of that depends on the mass. So it kind of makes sense here, right? You apply a force during a time t, then the velocity will change depending on the mass. This term here, he called that the change in momentum. Okay, so we're going to see that next unit, but momentum is the mass times velocity. A change means final minus initial, right? So it's final momentum minus initial momentum. So if you apply a force during a time t, consequence will be a change in momentum. Or if there is a change in momentum, then there will be a force applied during a time t. If the time here is very small, the force is very large. Okay, we saw that with the what it's called, the seat belt, the what is called the pillow, right, to stop airbag. Thank you. We saw that with the airbag, right? So if the time is very small, it's gonna hurt. But if you increase the time of impact, the force will be smaller. Okay, we're gonna see that quantity here is called the impulse. So if there is an impulse, then there is a change in momentum. So anyway, that was written this way in Principia. And then if you massage a little bit the equation, you divide by the time on both sides, then delta v over delta t is the acceleration. So m times the acceleration. I use delta, but I really should be using the derivative, right? Should be like this, delta v over delta t. That will be more for an average acceleration, but in our case, we don't care because usually acceleration is constant. So that's Newton's second law. Okay? Any question? You can go from here to there if the mass is constant. If you have a rocket, for example, burning fuel, then it's more complicated because the mass will change with time. So in that case, we suppose that the mass stays the same, that no fuel is burned. So that will be Newton's second law. Okay. So Newton's second law, the equation that we're going to use will be acceleration, okay, equals the net force divided by the mass. So what does it mean, the net force? It means you need to add, okay, you add vectorally all those forces. So forces are vectors. So now you need to use your skill to add vectors. So first you need to add all the forces acting on the object, and then you find the net force, and then you can find the acceleration. Okay, so don't forget what we have been doing again and again and again, right? So if you have two vector, that vector here, and then you have another vector there, you can add them up using two different approaches, right? So you can do tail to head, So you have your two vectors here, and you're going to put one vector on top of the other one. That's why it's called tail to head, and that will be your vector sum. So here you are doing it geometrically. If you want to do it algebraically, to find the x component of the sum, you add the component of the first one, so this one plus that one. The y component of the sum is the y component of the first one plus the y component of the second one. Okay, so don't forget, we have done a lot of problems with that. Anyway, if you are in engineering, you will have to take vector calculus at some point. The other way to do it, it's called the parallelogram method. So you attach them by their tail here. You make your parallelogram. So the opposite sides are parallel and equal to each other. And then the diagonal here will be the vector sum. Okay, there is a parallelogram here. Is that clear? So that's, we have done that many times. Okay, so let's take an example. Just do it geometrically here. Let's say you have a box. So this is a box on the floor. And let's say there is no friction. We don't worry about friction. And there is one student pulling the box in this direction, one student pulling the box in that direction. Can you draw the net force? Once you have the net force, you will have the direction of the acceleration. Okay, so net force equals mass times acceleration. And remember what I told you before. Acceleration is the net force per unit mass for 1 kilogram. Okay, so let's do that. My knees getting old. Let's do that geometrically first. Do it. Don't wait for me. Don't stare. Do it. So it's very basic, but you know, in physics, the most important is to understand the concept, and then everything else is stupid math. Okay, so first you can attach them by their tail. Okay, so I'm going to use the parallelogram. So I'm going to make parallel to this one, and then that will be parallel to that one. Okay, and then I take the diagonal. So that vector here, it's called the net force. So my net force here, it's a vector sum. It's going to be F1 plus F2. Do you agree? And then you have acceleration. Acceleration is just the net force per unit mass. Okay, so if the mass, for example, is 3 kilograms, then your acceleration is your net force, okay, and you divide by the scalar divided by 3. Do you agree? Okay, so what does it mean? It means that you're going to go 1, and then 2, and then 3. So here, that's going to be your acceleration. You see how it works? Now you can do it. You can do it using components, right? So you can say, okay, I'm going to work in an X, Y coordinate system. That's what we usually do because any motion can be decomposed into its components. So now we can say that the X component, okay, will be the X component of 1 plus the X component of 2, and then you divide by the mass. And the Y component of A, okay, it's going to be the Y component of 1 plus the Y component. So you decompose. So it's like for kinematics, when you are decomposing in X component, Y component. In dynamics, you're going to do the same thing. So in 2D, So you have two equations. You're going to have x component. The sum of all the x component is going to be mass times the acceleration. And the sum of the y component is going to be mass times the y component. Is that clear? You can always decompose what's going on along the x, what's going on along the y. Okay? And then your acceleration, of course, is a vector, right? So you can find the magnitude using Pythagorean theorem, and it has a direction. The direction will be always the same as the net force. Okay? Very important. Once you understand that, it makes so much more sense. An equation, you're good? So if you start from rest, so it means if the initial velocity is 0, of course, it means that as long as you are pulling, or as long as the kids are pulling, it will accelerate in this direction. If you start from rest, it means the velocity will increase at the rate of the acceleration. But if you are not starting from rest, it doesn't mean that you have to accelerate in this direction. Example, remember projectile motion? So I don't know how to make a gun, like BB gun, something like this. And you have a projectile here. And what it's going to do, it's going to make a parabola. Do you agree? So he wants to keep going, wants to be here. No, 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 no. You have to fall. I want to keep going. Stay here. No, 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 no. Now you have to fall. 1, 2, 3, 4. And I want to go. And no, 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 no. You have to fall, right? So it's gonna make a parabola. I mean, it's not great drawing, but you get the idea. But where is the force in that case? Down. Okay, the force is down. So the net force is down because it's gravity. But you see that the velocity here, initial velocity, was in this direction. So it doesn't mean that because the force is down, okay, the acceleration will be down. Okay, so the acceleration will be down, but the motion will not be down. Okay, it will make it like parabola. Okay, you see the difference? So it's like if you have the Earth and then you have the Moon, even though the force is in this direction, even though the acceleration is this direction, the motion is not in this direction because it had momentum to begin with. Okay, it wants to keep going in a straight line. No, you can't. You're gonna fall. I want to keep going in a straight line at a constant speed. No, you can't. You're gonna fall. Okay, so there is a conceptual question. So for the next test, make sure that if you didn't do it before, make sure you take screenshot of the pop quiz. Okay, so let's do very simple problem here. And the goal is to find the acceleration. Only the acceleration along the x. Along the x, you find the acceleration. So you have to find the net force. To find the net force, you can say along the x, right minus left. Okay, so that will be your net force along the x. Okay, so right minus x, left equals mass times acceleration. So this one is easy. So you can help each other. Do it, do it, do it. So we have F equals MA. Okay. So you can divide into components. So X component, Y component. And here it should be the net. So it means the sum, right? So that will be the sum. Net equals, and then here you have mass times acceleration, right? So m times the x component of the acceleration, y component of the acceleration. Okay, so in that case, it's easy. Is that clear? So do it. You have to use trig. Maybe this is not great. You can decompose your motion. That's maybe easier. And your motion. Dun, 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 dun. Along the y equals mass times the acceleration along the y. Okay, so number one is easy. I'm going to use along the x-axis, okay? I don't want to know about the y-axis along the x-axis. So case number one, there is only F1. Do you agree? So F1 equals the magnitude. It's positive here. It's positive. It's to the right times mass times acceleration. So in that case, it's only F1, right? Not yet. Not this one. This one. What? Huh? Yes, this one, yes. Not that one. So you have three cases. So this is just the first case, right? The first case, there's just one force applied. Okay. So F1 is 4 equals 0.2 times the acceleration along the x. So the acceleration equals equals 20. So this one will accelerate at a constant rate if the force is applied. As long as the force is applied, it will accelerate. Okay, what about B? About the x-axis. So I'm going to do it this way. I'm going to say whatever is pulling right minus whatever is pulling left. That's easier to remember. Equals the mass times acceleration. And if you use this way, you're going to use only the magnitude. So what is pulling at right? It will be for left. This one is opposing. So I'm trying to find the net force equals 0.2 times the acceleration. So the acceleration will be 10, you're right. Okay? Now, this one, you see, you have a force, F sub 3, but it has, go away, no, stay, no, go away. It has two components, right? There is one component that will pull to the right. That will be its job. Okay, so that component is how much of f of sub 3 is along the positive x, and it has a component along the y. And we don't care about this one. We only care about that one. Agree? We have to decompose vectors into components. So if you have two components, you're going to have two equations. But I am only interested into the x component. Okay, so you have, we're going to say right minus left. Going to do the same thing, equals mass times acceleration along the x. What is pulling to the right? Is it f sub 3 or f sub 3x? 3x, very good, right? Because f sub 3x is how much of f sub 3 is pulling to the right. They ignore each other. Exactly. So we're going to use cosine. Do you all agree? Because that will be the adjacent, right? We have a right angle triangle, hypotenuse. This is the angle, so that will be the adjacent. Minus to the left is 2 equals 0.2 times the acceleration. Do it, do it, do it. Take your calculator. If you don't have one, use your phone. Negative 5 points. So what does it mean? It's negative. It means that maybe it was moving in this direction, but it's going to slow down. Okay? Because if it was moving to the right, it's going to slow down. If it was not moving to the right, so it's moving to the left. It's going to accelerate at left. So if you start from 0, if it was not moving at all, you see this one is the winner. This one is the loser. So it's going to move to the left. Okay, so it's going to accelerate at left at a constant rate. Okay? Okay, so this is a misconception. A force does not cause motion because according to Newton's first law, if something is moving, it wants to keep moving at the same speed in the same direction. A force will just cause a change in motion, speeding up, slowing down, or turning, a change in velocity. So this is a misconception that lasted up to Galileo because Aristotle didn't agree with it, right? So he took Galileo and then he took Newton to put everything in math. So it's not intuitive. So with Newton's second law, we're going to work in 2D. So you will have to do along the x and along the y. So you can say right minus left equals mass times acceleration, up minus down equals mass times acceleration. You find the acceleration with its components, and then you can find the acceleration with the magnitude and Pythagorean theorem and everything else. So conceptual question, does the object has to move in the same direction as the net force? No, very good, because if it had momentum to begin with, along the x, for example, with a projectile motion, it wants to keep moving along the x at the same speed, and at the same time, it will accelerate down. So you have to combine those two motions. Okay? This is easy. So with the same force, if you multiply the mass by 2, what's going to happen? V, exactly. Right, so multiply by 2, the mass acceleration will be divided by 2. It's a proportion. Okay, it's moving at a constant speed. Which one is... So if it's moving at a constant speed, it means the net force is 0. Why? It's not that obvious, but let's say you are jumping. Exactly. Okay. So for example, if you are jumping from an airplane, you see at the beginning, your acceleration is g. But as you're gonna move faster, air drag will build up. air drag, there is an equation for it. Air drag will be proportional to the speed square. So as you're gonna go faster, okay, the air drag will build up even more. At some point, you're gonna reach terminal speed. Does it mean that you stop moving mid-air and people say, hey, what you doing? No, you keep moving, right? But the net force is zero because weight equals to drag. So if the net force is zero, you are either at a constant velocity or not moving. Obviously, here you are at a constant velocity, you have reached terminal speed. Okay, it's not that obvious. So the answer is B. So let's do from your book 4.4. I think it's an easy one. It's just to make sure you know how. Oh, by the way, you have to open your textbook, blah blah blah, and study and blah blah blah. Especially if you want to be engineer, blah blah blah. What's going on? A worker applies a constant horizontal force to a box. Okay, they already kind of, so they kind of did the drawing for you here. So you are pushing a box. Okay, so there is no friction apparently. And you also have a force up and down. So that will be the weight. The weight is always pulling down toward the earth, the center of the earth. That will be the support force. Otherwise it will break the floor. So the floor has to push back. Are these forces, is there a force larger than the other one? No, okay, so it's not going up or down. Only along the x do we have an unbalanced force. So we're gonna apply Newton's second law along the x-axis, right? Okay, so right minus left equals mass times acceleration. There is no left because there is no friction. There is only one push. So 20 equals 40 times acceleration. So acceleration will be, yes, 0.5. So what they did here, it's called the free body diagram. Because physicists, they don't know how to draw. So what they do a XY coordinate system here. And your box, your mass, becomes just a dot. So they will put a dot here. And then they say, okay, what are the forces acting on it? You're going to have a push here, 20 Newton. You're going to have the normal force, it's called, or support force here. And you have the weight. Okay, and that will be the mass. So this is called a free body diagram. Also in physics, it's very important to isolate the system you are looking at. So it means you have to make a bubble here. That will be my bubble. This is what I'm looking at. And it's being applied by 1, 2, 3 external force. Okay, I'm not interested in this person here because he's going to be pushed back. You cannot push without pushing. So the box is going to push back on him or her with a force of 20 Newton. Got that? It's very important. Okay, now it's a her. Right? So she will experience a force here of 20 Newton, exactly 20 Newton, because you cannot push without being pushed back, but we don't care about her. We just care about that system here. Okay? It's not that obvious what I say. 4.5 from your book. Okay, so this one combined kinematics and dynamics. So waitress, why is that a waitress and not a waiter? So he is pushing a bottle here. Initial velocity is 2. So she push here over there. She's tired, you know. Here your thing, leave me alone. So it's gonna stop there, right? And that will be the distance covered. So this is kinematics. So first you're gonna find the acceleration. And why is it stopping? Why do you think it's gonna stop? Because of the friction. Kinetic friction, because it's moving, it's sliding, so it's called kinetic friction. So the first step is to find the acceleration. Once you have the acceleration, you can find the force, F equals ma. But first you need to find the acceleration using kinematics. Everyone understand the situation? So first use kinematics to find the acceleration. Once you have the acceleration, then you can find the force. Okay, do it. More you do it. Do. So first we do kinematics. Okay, so we have the initial velocity is 2. Final velocity is 0. And displacement along the x is 1. And we need to find the acceleration. So 1, 2, 3. So which equation you can use? Yes, exactly. So it's going to be a final square equals initial square 2 square plus 2 times displacement times acceleration, and final is 0. So acceleration is very good. -2. Okay. So once you have the acceleration, you see there is a force of friction. Actually, the frictional force is between the surface and the object here. So you have kinetic friction. So we can say, okay, so you can write right minus left equals mass times acceleration. There is nothing right. So minus the force of friction. So that will be the magnitude equals the mass 0.45 times -2. So when I use this is just the magnitude, okay? Minus 0.9 Newton plus in magnitude. So this is in magnitude, okay? When I use this, that will be the magnitude. This is the magnitude. So the force of friction has a magnitude of 0.9 unit. Which way? Left. Or I can say minus 0.9 Newton. So here it's just the magnitude because you already have your minus here. If you do it this way, okay? So these are very, very basic, okay? Very simple. But once you understand the basic one, okay, from your book, now you have, it's an ice boat. The ice boat is pushed by the wind and you have friction and you have the acceleration. So it's an ice boat. I don't know. So you have the wind pushing, and you have the drag between the ice and the boat, and the wind is 100 Newton, and the acceleration is, I don't know, 1.5. Acceleration is 1.5, and the mass is 200 kilograms. 1.5, 100 Newton, and the mass is 200 kilograms. Okay, so they want you to find the friction. So right minus left equals mass times acceleration. Right, 100 minus friction, magnitude, equals 200 times 1.5. So friction equals 100 minus 300. No. Yes? Okay. So it's going to be minus 200 Newton. Okay. It should be so that will be 200 Newton, right? Was it what they ask you or what? No, they want you to find. Well, anyway, I changed the problem. It's okay. I think I did a mistake, but the methodology is the right one. Okay, so the first law of Newton, we have seen it's a special case of the Newton's second law. You have to go over that problem, okay? Because I didn't follow the book. Do you want me to go over it? No, now it's getting on my nerves. So what was the friction is given. The friction is 100 Newton, and you want to find the force of the wind. We did it backwards. So I did it wrong. I want to make sure. So erase whatever. So this is 1.5 meter per second per second. The friction is 100 Newton, and this is IDK. Okay, so then you have right minus left equals mass times acceleration. So that's the wind minus 100 equals the mass is 200 times 1.5. So the force of the wind is 300 plus 100. So it will be 400 Newton. Okay, so erase what I did before. Right. But the one I did before, you have friction larger than the wind. No, so now no, not possible. You cannot have the friction larger. You cannot have the friction larger. The maximum friction will be equal to the force applied by the wind. Okay, so erase, rewind, back. Is that clear? Okay, so this is a nice example because it's not that obvious. I don't know where I am now. So in that case, where is the net force? Is there a net force? Is the net force zero? Is it up or is it down? Down. So the acceleration will be down, almost equals to the acceleration due to gravity. Okay, so about 20 miles per hour per second. Now, what's happening to the acceleration? You still have an acceleration, but decrease. Very good, very good. So does it mean that you're going to slow down? No, it means very good, speed up, but at a lower rate. It's like inflation. They say, oh, inflation decrease. Excuse me, if you have 5% inflation and then you have 3% inflation and then 2% inflation, you still have inflation. Okay, it's the rate at which it's increasing. But if you go to Costco, for example, look at the price of the food, obviously it doesn't decrease. Maybe it's not going to decrease as much, but it's still increasing. Okay. It's not that easy to understand because they always say, oh, inflation is decreasing. No, 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 no. It's the rate. It's the rate that decreases. So here it's the same thing. The speed is increasing, but at a lower rate. At that point, what is the acceleration? Zero. So now she has reached terminal speed. Okay. And the best way to show that is when you are an engineer, you want to make a graph, right? So let's see what type of graph do we get. Um, okay, so you have a parachute, and in red, you see acceleration start to be 10. Okay, so first it's 10. And then the acceleration is going to decrease, 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 and then it gets to 0. The speed, you see the slope here is going to be 10. The speed of the slope of the speed is going to be 10. But the speed is still gonna increase, but at a slower rate because the slope is decreasing, 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 decreasing. And what is the slope here? 0. Very good. Okay, so here the slope is 0. Gravity is always the same. Okay, the weight is always the same. What's happening to the drag? The drag goes with the speed square. It depends on the surface area, but it depends on the shape of the object as well. There is an equation for that, and it depends on the density of the air, but it goes with the speed square. And you see the drag increase, increase, increase until it's going to match with gravity. It cannot go over gravity because otherwise it will go up, which doesn't make sense, right? Of course, it depends on the mass, right? So if you increase the mass, it will make harder for air resistance to match. So it will take longer to match. So if you have something very heavy falling, like a coconut falling from a palm tree, you won't notice air resistance because it doesn't have time to build up. Okay. A lot of applications. So I'm sure those who are working in biology lab, you have done that. Okay, it's a technique to separate DNA fragments and the air resistance, as I told you. So here you are not using the mass, you are using the shape. Okay, air resistance depends also on the shape. So you have all those fragments of DNA, and DNA is charged negatively. I have to Google it because I don't know about biology. I mean, I know, but I forget. I don't know why. But the fragments are charged negatively. Is that right? Something phosphate. because of the phosphate. Isn't that right? The phosphate is negatively charged, right? Okay, thank you. So negative, and then you apply an electric field. So they all want to go to the positive, toward the positive electrode, right? And here you have some kind of gel, something viscous. So they all move, but the largest fragment will be left behind and the smallest one will be ahead. So it doesn't depend on the mass. In that case, it's the shape of the fragment, right? Yes. Yes, yes. So if you, so here actually it's a good question. You have your fragment here. There is a force QE, and you have the drag. So if you, so the force is the charge, which is the same for all of them, times the electric field. So if you increase the charge here, you increase the electric field, so you will have more force in this direction. Drag because of the gel. Yeah. And they reach terminal speed at some point. Okay. And there is an equation for the drag. You might want to look it up. Now I think with a gel, when it's viscous, it depends on the speed, but also on the shape. So here is another technology here. They also, so they use that, it's called a drift tube to separate components. So they have to ionize them, and then you have a drift gas here, and you have ions coming in this direction. So the largest one will lag behind because it depends on the shape. So again, you have two forces, the electric force here and the drag. They use that on a planet, Europa. Europa is not a planet, it's a moon. And they sent, I don't know if it's there or not, but you have some kind of space probe collecting all the kind of stuff you have on that moon, and they have this device to detect whatever molecules you have. So you can look it up. Okay, let's do this. This. Come on, come on, come on, come on, come on. You have different way to do it. Okay, you can do it. You can do it you can do it the way you want to do it. Yeah, don't wait for me, right? You always draw. So this is your object here, and then east is this way. So 300 here. Bless you, 700 there. 500. So you have different way to do it, okay? Bless you. So you can do it you can do it in your head. But I'm going to do it the long way. So F1 x component 0. F2 0 x component 700. F3. I always change my method, so don't do it as you want to do it. And F4 0 minus 600. Okay, so the net force is the sum of all the force. So x component will be 300 minus 500 is minus 200. Y component will be 100. You don't have to do it this way. You can look here. 700 minus 600 will be 100. 500 to the left minus 300 to the right will be 100. So acceleration is the net force divided by the mass, and the mass is 4 kilograms. It's going to be minus 200 divided by 4 is negative 50. And 100 divided by 4 is 25. And then you do Pythagorean theorem. So this one, so it means x components and y component. So that's going to be your acceleration here. Oh, yeah. I was checking if you were paying attention. Here. So acceleration x component minus 50, 20, 25. Do you agree? You see the tail of your vector is always a coordinate. So acceleration has a magnitude of whatever this is. And we need to find the angle. I'm going to tan. So this is 25 over 50. What's going to be the magnitude? 56. So 56 meter per second per second. That angle here, so this is theta, it's going to be tan minus 1. Opposite is 25 over 50. (26°), but this is this angle here, so you have to do 180 minus, yes. So 153. 153. Do you agree? For those that I have lost on the way, I'm going to make my drawing a little bit better. Okay, so you have your x, y. So that's going to be 25. That's going to be 50. So that will be your vector A. And that angle here is what? 27 degrees. This is 27 degrees. So if you want to find that angle here, you have to do 180 minus 27. Okay? Uh, Is that clear? Okay. Newton's third law. That's not something that is intuitive at all. It says that you cannot push without being pushed, but you cannot push harder than you are being pushed, and you cannot be pushed harder than you are pushing. It's not obvious, right? So it means that if someone is really strong, really strong, and that person is pulling me, the force experienced will be always the same. The consequence is not the same. Which means if you have a truck, like a Mack truck, a heavy truck, colliding with a bike, for example, no one is harmed in that experiment. So they collide with each other. The force experienced is the same, but not the consequence. So of course the acceleration will be very small for the truck and huge for the bike. Okay, so you always have this experiment here. You have like, you can measure the force here. You're gonna read, okay? Read whatever. I need someone. Let's say we are as strong. Let's pretend. Do you see the same thing? About same reading? Let's go. About the same reading. Opposite side, that's opposite reading. Do I have to do it this way? No. Okay, opposite side, the same reading. Do you agree? Now it's stronger. Pull. 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 But do you see the same reading? Pull. But not pull. The same reading, right? But is the consequence the same? No, because I'm losing. So I'm gonna move back, but the force is the same. Right? Thank you. So the consequence is not the same, but the force that you release is the same. You cannot pull without being pulled, and you cannot be pulled without pulling. The force is always the same. It's not intuitive. So you see here, you can put an elephant if you want. Maybe the elephant will win, obviously. So you're going to move. So your acceleration will not be zero, but the force is always the same. Okay? So here, he's pushing the Earth spacecraft. Okay? The push is the same, but this one has a huge mass. So its acceleration is going to be small. So it's going to barely move. This one, okay, is going to experience the same push, but because his acceleration is very small, what's going to happen to him? He's going to move, he's going to recoil, he's going to move back. Okay, so I had a student like long time ago, long time ago. Here, she was great, and she did that experiment with her dad. So they took two bathroom scale, and they pushed on both sides, and the reading was the same. And then the dad pushed harder, so she moved back, but the reading was still the same. It's not that intuitive. And she did the edit. So you can do that experiment if you want. So it's not obvious, right? The consequence is not the same, but the push or the pull. So you always have a conceptual question about that. Okay, don't let me trick you. The push or the pull is always the same, not the consequence. So for example, I am, sadly, I cannot lose weight, 180 pounds, even more. I'm not going to tell you. 180 pounds. So what does it mean? It means the earth is pulling me with 180 pounds. Do you agree? What's the reaction? I am pulling the earth with 180 pounds. I have this power. I'm pulling the earth with 180 pounds. If I was to step on this desk, okay, and I jump, the earth is jumping toward me, okay, because I'm pulling on the earth with 180 pounds. The force is the same, not the consequence. Of course, the earth is not going to move because it has so much mass. I am going toward the earth, even though I'm pulling it with the same force. So the force is the same, not the consequence. So you might think because other people here are pulling on the other side of the earth. No. Okay, so this is also this is a famous misconception, so I will go back to this. So lift, for example, also you can think of it as the Newton's third law. You push on the air is going to push back on you. Okay, it's Newton's third law. You cannot push without being pushed back. Another example, here that used to be the space station, and the space station or the shuttle, space shuttle, right? And so fuel is being burned. So the space station is pushing on the exhaust gas. So the exhaust gas is pushing back with the same force, but the acceleration is not the same. Because the mass here is so big, the acceleration will be about 3g. Anyway, you don't want to be more than 3g because the astronauts, not going to feel very good. But the gas here will have a huge acceleration. So the force is the same, but not the acceleration. That's how airplane work, right? They push on the air push back. But in space, there is no air. So you have to push on the gas here that you burn, exhaust gas. Push on the gas is pushing back. The force is the same. The space shuttle has a huge mass, a small acceleration, and the gas has a small mass and huge acceleration. Okay? It's not that obvious. And then you have to be careful. So typical also conceptual question. You have, so the action reaction goes always with two objects. So for example, you have the apple here. So you have the pair apple table. So what's going to happen? The apple, because of the weight, is going to push on the table. So that will be the table, the weight of the apple is pushing on the table. So the table is going to be pushing back on it. At the same time, you have the earth, right? So the earth is going to pull the apple down. So the apple is going to pull the earth up. So you have apple table and you have apple earth. So it's you and me. I push you, you push me. There is no ménage à trois, right? So law is the same. It's not that intuitive either. No ménage à trois. It's only for the French. So you push the wall is going to push back on you. And the force is the same, not the consequence, because of course the wall has a huge mass. If you're not convinced, you can punch. See how it feels. Right? So the force will be always the same. Okay, so one example, we already talked about that. It's called the Magnus force, right? So if you make, so this one will be, you have a top spin and a bottom spin. So if it's gonna spin this way, so you are throwing a tennis ball and you make it spin, this is called a back spin, not a bottom spin, a back spin. You make it spin this way, okay? So what it's gonna do, it's gonna deflect the air down. The air is gonna be deflected down, so the air is gonna make the ball go up. For every action, you have an equal reaction. So in that case, you have a top spin, okay? So it's making the air go up, so the ball will go down. You can do it also with a football here. So this is called the Magnus force. And there is, let's see, action, reaction. There is a famous demo. Yes, thank you. Thank you, thank you. What's your name, Michael? Yeah, you can try to do it. You can do that.
A friend of mine went to an Oregon dam and which is 126.5 meters or 415 feet high. Then they dropped a basketball over the edge. You can see that the basketball gets pushed around a bit by the breeze, but it lands basically right below where it was dropped. Now watch what happens when they drop another basketball, this time with a bit of backspin. Whoa, look at that go! I don't know what. This is Brett who just threw it. I literally just dropped it with a bit of spin, like I didn't even throw it, and it just took off. Like I had no idea. This is where I come in. The basketball was subject to the Magnus effect, which affects all rotating balls or cylinders as they fly through the air. And it works like this. As the basketball picks up speed, air on the front side of the ball is going in the same direction as its spin, and therefore it gets dragged along with the ball and deflected back. Air on the other side is moving opposite to the ball spin, so the flow separates from the ball instead of getting deflected. The net result is the ball pushes air one way, so the air applies an equal force on the ball the other way. And this is known as the Magnus effect, named after Heinrich Gustav Magnus, who described it in 1852. Of course, Isaac Newton beat him to it by nearly 200 years, describing the flight of tennis balls at Cambridge College. But, he's got enough stuff named after him. This effect is very important in sports like tennis, soccer, and golf. But could it have non-sport applications? Perhaps. This is a sailboat. I know it doesn't look like a sailboat, but those aren't chimneys. They are spinning cylinders called Flettner rotors, and they take the place of the sails. They deflect crosswinds using the Magnus effect to propel the ship forwards. And this is a plane with spinning cylinders instead of wings. Using the Magnus effect, the cylinders actually generate more lift than traditional wings. However, they also generate way more drag, making them impractical. This plane only flew once and then it crashed. But the Magnus effect is making a comeback. Here is an experimental rotor wing aircraft which generates all its lift from spinning cylinders. And this is the E-Ship 1, which uses 4 spinning cylinders, that's 4 Flettner rotors, to increase its efficiency and reduce the amount of diesel it burns. So in the future, the Magnus effect may help more than just basketballs fly.
Okay, it's a cool video, right? It's the YouTube channel Veritasium. Veritasium, right? Action, reaction. And I show you what I did at the gym. You can do that. I I know if I want to go back. You remember? Okay. You can go back to the first video. Ah, this one also. You can do that with a bowling ball. You see? Okay, that's cool. Okay, so the question here, if you have a truck and a small car, if they collide, what is true? Hey, very good, right? It's not intuitive. They experience the same force, not the same consequence. If you play a tug of war like I did, the same force, okay, same pull. An apple, what is the reaction? The earth pulls on the apple is going to pull back on the earth with the same force. A hammer hits a nail, so the nail is going to hit back the hammer. So it's the helicopter push air down, the air is going to push it up, very good. And so for every action, you have a reaction. So example here, that was my favorite movie back then, right? The force is the same, always the same, not the consequence. Okay, the force is the same, but Baloo has a huge mass, so very small in velocity change. Mowgli has a small mass, so huge acceleration, huge change in velocity. You exaggerate. What time is it? It's 11:52.
I understand. This morning, one of my family members left the boot camp.
Okay, but
And I was
try to be on time, right? Next time. So you can take this equation here, you divide by the time both sides. You see what you get? Next time I will remove attendance. Okay, so the force is the same. So you're going to have the same force. Same force. Big mass, small acceleration. If you have a small mass, you have a big acceleration. Acceleration, that means a big change in velocity over the time. Okay, so force is the same. Huge mass, small change in velocity, and the time is the same. Do you agree? And there is a minus here, and there is a minus there. So because the time is the same, we can say bye-bye to the time. So what do we get? We're going to get that a change mass times a big change in velocity equals minus, that will be a huge mass over the change in velocity. Do you remember what is m delta v? Momentum, exactly. This is the conservation of momentum. Okay, the momentum, the change in momentum will be the same for both systems interacting with each other, but it depends on the mass, right? Okay. So the change in momentum is the same for both of them, but because the mass is small, the change in velocity is huge. So this is called conservation of momentum, and that was understood by Newton. He called momentum the quantity of motion. So it's not obvious when you have bugs crashing on your windshield. Is the force the same? Yes, the force experience will be the same, not the consequence. Obviously, you don't want to be a bug. Right. A cell phone is sitting on the desk. The desk, the desk, the desk, the desk. What is the reaction? the normal force of the table on the phone, because it's always two, the same two objects, no ménage à trois, okay? So Earth is not involved here. You exert a force F on the bookcase exert on you will be negative F, right? You cannot push. Exactly. Cannot push harder than you are being pushed. And this is a paradox here. You might think, okay, this horse is not going anywhere because the wagon is pulling this direction, and this going this way, and that going that way, and that going that way. It's not going to go anywhere. So in physics, you have to be very careful to define your system. So we don't want to have action, reaction apply to the same system, because action and reaction do not apply to the same system. So here you have the horse and the ground. So the horse pushes the ground is going to push back because of friction. And then you have the wagon pulling back the horse, and the horse is pulling the wagon. But we take one system at a time. So we're going to take the horse. If you look at the horse, there are only two forces acting on it. Okay, so these are called external forces, right? So if I make a free body diagram, see you have the ground pushing the horse, and you have the wagon. So if they are equal to each other, maybe it's going to be at rest or moving at a constant velocity. And then you have this system here. So exactly. So there is only one force applied to it. If you neglect, because it's a wheel, so a wheel you only have static friction. It's not that much. It's going to accelerate. And then the ground, it's another system. And of course, the mass is so big, it's not going to accelerate. So you really have to define your system and the external forces. Do you agree? So it's called the horse wagon paradox. So for example, here it's a typical question, typical on the final or test 2, I forgot also, because you see you are pushing two books. But if you are only taking this one, what is the force acting on it? No, not from the hand, because the hand is not touching it, right? The push from the other book. Okay, so this is not obvious. You have the mass 2 and that mass 2. So that book here is being pushed by the other book. It's not obvious. Now, if I take only this one, it's being touched by what? It's being touched by the hand. Okay, so you have a force in this. Exactly. And it's being pushed by the other book. Do you see? So this is action, reaction. I push you, you push me. And if I take another color, if I take here, if I take those two books all together, I don't care what's going on. I don't want to know their relationship between them. It's private. You don't want to know. But if you take that system here with M1 and M2, what's the only force acting on it? The hand. That will be your external force, right? Of course, they have some kind of relationship between them, but we don't want to know because it's inside, so not your business. Don't look. You just want to know the external force. Okay? Really? Can you send me the video? Yeah, a canvas goes to my email. Thank you. Okay, so types of forces that we look at. You have the drag force, apply force, the weight, frictional force, spring force is from a spring. Forces at distance, tension along a rope, buoyant force, anything submerged, emerged, or submerged will be acted upon by a buoyant force, right? Okay, so this one is easy to understand. That will be your weight. Okay, so the weight is the pull from the earth. It's like the earth grabs you, pulls you toward its center. So we can say the weight equals mg, right? So that will be the pull from the earth. This is a constant. That's the mass of the object being pulled. That will be the mass of the earth. So this is equals to mg. And g is 10 meter per second, and that will be the mass. So that here is g. So it's a constant times the mass of the earth divided by the radius of the earth square. And this is a constant. You don't have to worry about it too much. It's very small. It's very small because that means gravity is very weak. That's why we can walk around, right? Okay. F equals mg.